Hello everyone, in this video we will cover the section 4.2. In this section we will consider the nth order linear homogeneous differential equation with constant coefficients. So the general form of such an equation can be written in this form. The coefficients are constants, real numbers, and here a0 is not equal to 0, which is the coefficient of the highest derivative in the differential equation. So we will try to find the solution of such equations by considering the previous chapter, the preceding chapter. You know, for second order linear homogeneous differential equation with constant coefficient, we find the characteristic equation first of this equation, and then after solving the characteristic equation, namely after finding the roots of the characteristic equation, according to the type of the roots, it can be two different real roots or complex roots or equal roots. So similarly, to find the general solution of this equation, we will follow the similar idea. So the constants are real constants, real numbers, and the coefficient of a highest derivative of the dependent variable is not equal to 0. So to find the solution, as I said, first we need to find the characteristic equation. This is the nth order linear homogeneous differential equation. Like the second order, we take the coefficients and the highest derivative. So we have nth derivative here. So the degree of the characteristic polynomial will be also n, by writing r to the power n, okay, plus a1 r to the power n minus 1 plus a2 r to the power n minus 2, and so on. Okay. When we consider the last two terms here, so we write a n minus 1 r plus a n is equal to 0. So here we should find the roots of this characteristic polynomial of the linear homogeneous differential equation, and then according to the type of the roots we will write the general solution. Some of roots can be real and different, some of them can be complex, and some of them can be equal to each other, can be repeated any times. Therefore, if you have real and different roots for the characteristic differential equation, like R1 characteristic equation, R2 blah blah Rn, for example, we can suppose that all of the roots of this polynomial equation have it can be real and different. So in this case, the general solution or the special solutions, the corresponding special solutions will be e to the power r1t, e to the power r1t, e to the power r2t, e to the power r3t, and so on. Okay. If the roots are real and different from each other, so the special solutions will be like that: e to the power rnt. If they are different, if you have equal roots, namely any root of this characteristic equation is repeated s times, for example, r is a root repeated s times or so we can write the corresponding solutions, special solutions, as e to the power r times t, t times e to the power r times t, t squared times e to the power r square r times t, sorry, r times t, and until t to the power s minus 1 e to the power r times t. So we will have s special solutions for the root repeated s times, namely the factor of the characteristic equation will be r minus if we say this is let's say rs, because the variable of the characteristic equation is also r, therefore we should use another expression for the repeated root, and we say this is rs. So the factor of the characteristic equation, one of the factors, can be written as r minus rs to the power s. Okay. In this case, the corresponding special solutions of the homogeneous differential equation will be like that. Okay, and you can see in the lecture note here. This one, if for an equation of order n, if a root of the characteristic equation, say r1, has multiplicity s or is repeated s times, and s should be less than or equal to n, namely should be less than the degree of the characteristic equation, and they are written here, they are corresponding solution of the equation, okay, when we have repeated roots. Of course, when we have complex roots, so we will use the formula, if you remember, for example, alpha plus minus I beta is complex conjugates for example of the characteristic equation, so the corresponding special solutions will be, you know, e to the power alpha t times cosine beta t, and e to the power alpha t times sine beta t. Okay, and the most general form, the most general statement for the solution of the differential equation here will be a linear combination of them. Okay, if sum of roots are real and different, so we will use this formula. If sum of roots are repeated, so we will use this one, and if sum of the roots are complex, so we will use these formulas. Okay, and lastly we will write a linear combination of them to state the general solution of this differential equation. For example, Let's solve an example about that. Find the general solution of this differential equation. The fourth derivative plus the third derivative minus 7 times the second derivative minus the first derivative plus 6 times y is equal to 0. And we have also the initial conditions for this differential equation here. So first we should write the characteristic equation of this differential equation. Fourth derivative plus the third derivative minus 7 times the second derivative and first derivative minus the first derivative plus 6 times y is equal to 0. So the corresponding characteristic equation is written as r to the power 4 plus r to the power 3 minus 7 times r square minus r plus 6 is equal to 0. So here we should find the roots of this characteristic polynomial. I guess we should write the term r cube and minus r together, and the remaining terms will be another group here, namely r4 minus 7 r square plus 6 and plus r cube minus r is equal to 0. When we consider the first group here, the factors of this first one will be r square minus 1 r square minus 6. And when we consider the second group, so we can write r times r square minus 1 is equal to 0. So from here we obtain r square minus 1 times r square plus r minus 6 is equal to 0. And from here we obtain r minus 1 r plus 1. From the second term we have the factors r minus 2 r plus 3 is equal to 0. So here we have 4 different real roots. The first one is 1, the second is minus 1, the third is 2, the last is minus 3. Therefore we use the first formula written here when we have different real roots. So the general solution, and we don't have any complete root, we don't have any repeated root for the characteristic polynomial of the differential equation. Therefore the general solution easily is written as c1 times e to the power r1t, which is e to the power t, plus c2 times e to the power minus t, c3 times e to the power 2 times t, and c4 times e to the power minus 3t. Okay, this is the general solution of the differential equation, and we can check this by finding the Wronskian of the special solutions: e to the power t, e to the power minus t, e to the power 2 times t, and e to the power minus 3 times t also. And here you can see the answer also. And we have the initial conditions for this differential equation, which means we can also find the constants c1, c2, c3 and c4 the initial conditions require that C1 and C4 satisfy the four equations. After finding the first, second, and third derivatives of this solution function and writing the initial conditions to them, so we obtain four equations related to the constants. And by solving this system of four linear algebraic equations by remembering the linear algebra, so we find the constants like this one, and writing to the general solution, actually we will have exactly one solution for this differential equation, which is written as 11 over 8 times e to the power t. Namely, the solution can be written as 11 over 8 e to the power t plus 5 over 12 e to the power minus t plus minus 2 over 3 e to the power 2t minus 1 over 8 e to the power minus 3 times t. This is the exact solution of the differential equation given here. That's it. So if you are faced with the need to factor that characteristic polynomial by hand, here is one result that is sometimes helpful. Suppose that the polynomial has integer coefficients, namely we have integer roots for this this characteristic polynomial. So in order to find the roots, we have a method written here. I will explain by an example. For example, let's consider the characteristic polynomial obtained in the previous example. So to find easily the roots of this characteristic polynomial without considering these factors, so we consider the coefficient of the highest degree of the variable r. Here the highest degree is 4. Therefore, we will find the coefficient of r to the power 4, which is equal to 1. Okay, which is equal to 1. And we consider the constant, which is 6. And then we will find r, which is p over q, is a rational root. Where p and q have no common factors, then p must be a factor of an and q must be a factor of a0. So we will consider the factors of the coefficients a0 and an. Okay, a0 and an. So the factors of the number 6, namely, actually we have 6 in the numerator and we have 1 in the denominator. 1 is the coefficient of r to the power 4, and 6 is the coefficient. 6 is the constant of the characteristic polynomial. So we will find the factors of them. So the factors of 6 will be plus minus 3, plus minus 2, and plus minus 1. Over the factors of 1 is plus minus 1. Okay, we have possibilities for the root of the characteristic equation. Can be 3 or minus 3 after dividing 3 and 1. Can be 2 or minus 2. Can be 1 and minus 1. When we look at the roots, so we obtain 1, minus 1, 2 and minus 3. These are included here, you see. Therefore, this method is useful to find the root of the characteristic equation. For example, let's find the general solution of this differential equation. Y, the fourth derivative of y minus 4 times the third derivative minus 4 times the third derivative plus 10 times the second derivative minus 12 times the first derivative and plus 5 times y is equal to 0. Okay, first we need to find the characteristic equation. So we have r to the power 4 minus 4 times r to the power 3 plus 10 times r squared minus 12 times r plus 5 is equal to 0. What is the coefficient of r to the power 4, which is 1? 1. So in the denominator we have plus or minus 1. They are factors of the constant, the coefficient of the term which has the highest power for the characteristic polynomial, and the constant is 5, and its factors are plus or minus 5 and plus minus 1. Okay, they are the integer factors of the number 5. So here we have 4 possibilities for the root of the characteristic polynomial, namely can be plus 5, can be minus 5, can be plus 1, can be minus 1. After finding the result of this division, okay, so we obtain these 4 different possibilities. So the most easy possibility is the number plus 1. When we write plus 1 here, so we obtain 1 minus 4, which is equal to minus 3, plus 10 minus 12 is minus 2. Here we have plus 5. So that's it. We found one of the roots. 1 is the root of this characteristic equation, which means actually it is the multiplication of r minus 1 times something, because 1 is the root of this characteristic equation. When we check this equation for minus 1, so we obtain 5 plus 5 for 2 first terms plus 1. Here we have minus 1 times minus 4 becomes plus 4 for minus 1. 10 plus 10 plus 12 becomes 22. So we don't have 0 for the result, therefore minus 1 is not a root. Similarly, you can check the others. When we write 5, so here we have 5 to the power 4 minus 4 times 5 to the power 3. So the factor of the second term is 4. The second term, this one is less than r to the power 4, namely 5 to the power 4. Therefore, for the first 2 terms, we get positive number. And here, when we write 5, so we have 25 times 10 minus 12 times 5, which means this one also becomes a positive number. Positive number plus positive number plus positive number is equal to a positive number, which means the result is not equal to 0. Therefore, 5 is not a root. Also, you can check minus 5 is not a root. So we have one possibility here. Plus 1, namely r minus 1 is the factor of the characteristic equation. So how can we find the other roots? So to find the other roots, we will use the polynomial division to find the second factor here. Therefore, we apply the polynomial division for this differential equation. So let's divide this polynomial by r minus 1. So r to the fourth minus 4 r cube plus 10 times r squared minus 12r plus 5 division r minus 1. So to get to obtain r to the 4, we multiply r minus 1 by r3, r to the power 3. So we get r to the 4 minus r to the 3. When we apply a subtraction, so we obtain, namely, this one becomes minus, this one becomes plus. So we obtain minus 4 times r to the 3 plus r to the 3 minus 3 times r to the 3 plus 10 times r squared minus 12r plus 5. Similarly, to get r cube, we multiply r minus 1 by r squared. Actually, we have minus r cube, therefore we should have minus we should have minus 3 times r cube. Therefore we should multiply r minus 1 by minus 3 r squared. 3 r squared. Therefore we have minus 3 r cube plus 3 r squared, and from here we have, when we apply the subtraction, so we have plus here, this one becomes minus, they are gone, and here we have 7 times r squared minus 12r plus 5. And to get r squared, 7r squared, we multiply 7r, so we have 7 r squared minus 7r. When we apply the subtraction, so we obtain this one becomes plus minus 5r plus 5, and to get minus 5, we multiply r minus 1 by minus 5, so we have minus 5r plus 5. So the we have 0 for the remaining of this division. So this is the factor of this second factor of the characteristic polynomial. Therefore we write this is actually the multiplication of the terms r minus 1 times r cube minus 3r squared plus 7r minus 5. Okay. Second, now let's find the roots of this one. Let's follow the same way. Namely, for the numerator we will find the factors of the constant. The constant is minus 5, and its factors are plus minus 5 and plus minus 1 over the factors of the coefficient of the term which has the highest degree of the for the characteristic polynomial. So we have r cube here, and the factors of the coefficient of this term is plus 1 or minus 1. Okay. And again we have 4 possibilities for this second factor for the roots. So plus 5 minus 5 plus 1 minus 1. Okay. Therefore, let's try the most easy possibility of them among them, which is 1 actually. When we write 1 for the second factor, so we obtain 1 minus 3. Let's write here again the second factor, r cube minus 3r square plus 7r minus 5. And they are the possibilities for the roots for this second factor of the characteristic polynomial of the differential equation. So we should get 0 after writing one of them for r here. When we write 1, so we obtain 1 minus 3 becomes minus 2, 7 minus 5 plus 2, so we get 0. So 1 is a root for this one. And without checking the others, directly let's divide. For example, when we check minus 1, actually we will not get 0, I guess. So let's again apply the polynomial division. 7r minus 5 over. So since 1 is a root, so one of the factors of this second factor of the characteristic polynomial will be r minus 1. Okay, again r minus 1. So to get r cube, we multiply by r square. R cube r cube minus r square. When we apply the subtraction, so we obtain, this becomes minus, this becomes plus, so we have minus 2r square plus 7r minus 5. To get minus 2r square, we multiply minus 2r minus 2r square plus 2r. When we apply the subtraction, we obtain 5r minus 5. And to get 5r, we multiply by plus 5. So we have 5r minus 5, which means we have 0 for the last one. So lastly, this characteristic polynomial has the factors. So we have r minus 1 at the beginning, times again we have r minus 1 from the second factor, r minus 1, times this one, r square minus 2r plus 5 is equal to 0. Okay, for the characteristic equation of the differential equation. So what are the roots? So we have 1 for the root, which is repeated 2 times. Okay, r1 1 has multiplicity 2. When we look at the second one, easily we can find the discriminant of them, of this equation. B square, which is 4 minus 4 times 1 times 5, which is equal to minus 16, which is less than 0, which means we have complex roots for this one, and it is found as r2 3 minus b, namely 2, plus minus the discriminant, square root of minus 16 over 2a 2a. So from here we have 1 plus minus, here we have 4i over 2 becomes 2i. So from here we have complex roots. So sum of one of the roots is repeated 2 times, which is a real root, and the other roots are complex. Therefore the general solution will be c1 times e to the power t. Okay, 1 is the root, 1 times t. Since it is repeated 2 times, the second solution according to the formula written here, s is 2, so 2 minus 1 is 1, so t times e to the power rs is equal to 1. Therefore t times e to the power t is the corresponding special solution for this repeated root. So we write c2 times t times e to the power t plus c3. So now we use the formula for the complex roots. You know, we have alpha beta here, e to the power alpha t times cosine beta t, e to the power alpha t times sine beta t. Alpha is 1, beta is 2 here. Alpha is 1, beta is 2. So we write e to the power t cosine 2t plus c4 times e to the power t sine 2t. Okay, this is the general solution of this differential equation. That's it. And you can also check whether this is the general solution or not for the differential equation by finding the Wronskian of the special solutions. You know, when we compute the Wronskian of these special solutions, namely we will obtain 4 by 4 matrix, since we have 4 special solutions, 1, 2, 3, 4. The first row will be formed by writing them, and the second row is corresponding to their first derivatives, and the next row is is corresponding to the derivatives of the previous row, and so on. And after computing the Wronskian, we will obtain 16 times e to the power 4 times d, and then we can say from this conclusion that this is the general solution of the differential equation. Okay. Another example: find the general solution of this differential equation and also find the solution that satisfies the initial conditions written here. Again, the characteristic equation you see is r to the 4 minus 1. So we have here r square minus 1 times r square plus 1. We don't need to apply the method because easily we can find the factors of this characteristic polynomial. Therefore, from here we obtain the roots are 1 minus 1, which is obtained from the first factor, and I minus I. And similarly, using the formulas, the related formulas, so the general solution of this differential equation easily is written as c1 times e to the power t plus c2 times e to the power minus t, c3 times cosine t, because alpha is 0, beta is 1, therefore we don't write e to the power alpha t because e to the power 0 is equal to 1 since alpha is equal to 0, and c4 times sine t, beta is 1 here. And if we impose the initial conditions, so we obtain the constants by using the initial conditions written here, you can find easily, after finding the first derivative, second and third derivative of this special solution and writing 0 for t, you can find 4 equations for the constants, and after solving this linear system, so you will obtain the values of the constants, and then the solution of the given initial value problem will be in this form. Okay, C1 is 0, C2 is 3, so we have 3 times e to the power minus t. C3 is 1 over 2 times cosine t minus sine t. Okay, easily you can find. And another example, find the general solution of this differential equation. So the characteristic equation is r to the 4 plus 2 r squared plus 1, you see easily. And we can find easily the factors. So this is actually equal to the multiplication of r squared plus 1 2 times. And from here we have, for the first factor, we have I and minus I, actually, because when we compute the discriminant, so we don't have r here, which means b is 0, minus 4 times a, which is 1, times c, which is 1, over 2a sorry, and from here we have minus 2, so from here we don't have any 2a, sorry, we use this formula for finding the roots. This is just the formula for the discriminant. So we have minus 4, which is less than 0, which means we have complex root for this one. So the roots r1, 2 is equal to minus b, which is 0, plus minus square root of discriminant, which is minus 4, over 2a. Over 2a, this is 4, and from here we obtain 2i, so we have plus minus 2i over 2, we have plus minus I. Similarly, we can find the same result for the second factor, so we have plus minus I, and from the second one also we have plus minus I, which means I is repeated 2 times, minus I is repeated 2 times. Therefore, when we consider the formula for the repeated roots, so first we write alpha is 0, beta is 1. So the corresponding special solutions are cosine t and sine t, e to the power alpha t is 1 and cosine beta t is cosine t. Since it is repeated 2 times, and the last 2 special solutions can be obtained by multiplying t. C3 times t cosine t, C4 times t sine t, since the complex root is repeated 2 times, plus minus I is repeated 2 times. Therefore, we obtain this general solution for the differential equation. Thank you very much.